All right, hello and welcome to the video lecture for Friday, March 2nd, T-Test Day 1. Glad you found everything okay. Let's go ahead and jump right into it. All right, so we've been building up to inferential procedures this whole time, right? We spent that first part of the class talking about descriptive statistics. Last couple weeks, we've been talking about hypothesis testing, those 5 steps of hypothesis testing. We applied them to the z-test. So the 5 steps of conducting a z-test, again, just the same 5 steps of hypothesis testing that we talked about before. The z-test, however, has some limitations. So for the limitations of the z-test is that you have to know the population mean and the population variance or standard deviation in order to do a z-test at all. So remember the z-test formula, right? Z equals capital M, which is sample mean, minus mu, which is mean of the distribution of means. And that, of course, is equal to the population mean. So you have to know that in order to do the z-test. All of that gets divided by sigma sub m, the standard error of the mean. And to find the standard error of the mean, that equation on the right there, right, is equal to the variance of the population divided by the sample size and square rooted. So to get that piece of the equation, you need to have the variance of the population. So you have to have those 2 pieces of information to do a z-test. Now, sometimes we have that information. So for example, we used one example last week or the week before about the SAT, right? The SAT, everyone who ever takes that, their scores are recorded. So the testing service that administers the SAT has population information. But more often when we're doing psychological research, we don't have that info. So often we don't know these. Sometimes we only know population mean, but not variance or standard deviation, for example. Most often we know neither of these pieces, so we don't actually have any population info for the same reasons we talked about in sampling and probability, where it's just virtually impossible to get population information, especially on the majority of psychological variables that we're interested in. So whenever you're doing a study on mood or helping behavior, that kind of stuff, you never know population information. So what the heck do we do then? Well, that's why we have other inferential procedures. So the z-test is just one inferential procedure we can use. We can also use the t-test, which is what we're going to talk about today, of course, and then following spring break. We also can use ANOVA, which is coming later on in the course, and a couple others as well. So these inferential procedures are used when you don't meet these basic qualifications of the z-test. So when you don't have certain pieces of population information, for example, that's when you've got to use a different inferential procedure instead. All right, so the agenda for this entire topic of t-test, today we're going to start talking about the single sample t-test. We're going to talk about estimating population variance, and we'll get a little bit into conducting a single sample t-test. After spring break, we're going to pick back right up on this with the last steps of conducting the single sample t-test and doing some practicing there. Then we'll talk about 2 different kinds of 2-sample t-tests, the dependent means and independent means, and we'll wrap up this whole topic by talking about t-tests in psychological research articles. All right, so let's get started with the single sample t-test with estimating population variance. Okay, so this term single sample t-test, this is what it means. So the single sample t-test is a hypothesis testing procedure that we use when we know the population mean, but we do not know the population variance. So whereas in the z-test you need both of these pieces of information, you can do a single sample t-test if you only know population mean, but you do not know population variance. So you've got one of those 2 pieces, you can do the single sample t-test. So for example, I adapted this from an example in the textbook, and we're going to circle back around to this after spring break and actually calculate it. We're going to use it just kind of frame this idea right now. So for example, say that the BSU newspaper reports that BSU students study an average of 17 hours per week, but you think the students in your dorm study way more than that. So you survey 16 of your dorm mates and find that they study an average of 21 hours per week. And you want to know, is this a significant difference? Because of course, this whole issue with probability, right, and with people is that people are messy. So that difference of 4 hours per week, we don't know, is that just happen to differ by chance, that your sample just happens to study a little more, but on average it's not a statistical difference rather, or is it a real difference? So you've got to do some kind of an inferential procedure to answer that question. So in this case, we do know population mean, so we know, thanks to the BSU newspaper, that BSU students on average study 17 hours per week. We can treat that as population data, but we don't know anything about population variability. So that means that we cannot use the z-test. Instead, though, we can use the single sample t-test. So again, we're going to use this example again. We're going to circle back to this after spring break and actually calculate it out. But this is just kind of framing it for us right now. So don't worry about remembering these numbers. All right. So the good news is that the single sample t-test works basically the same way as the z-test. So it follows the same 5 steps of hypothesis testing, but there are a couple little tweaks here when we're doing a t-test. So the main tweak is that because we don't know population variance or population variability, we have to estimate it. So we've got to estimate population variance in order to do the single sample t-test. So doing this is going to affect some of our other steps as well. So although we're going to follow those same 5 steps of hypothesis testing, they're going to be a little bit different when we're doing a t-test instead of a z-test. And we'll talk all about that. Let's start by talking about estimating population variance. So I just said we have to do that, but how? So the question is, how in the heck do we estimate population variance? Well, the only variability information we have when we're doing a single sample t-test is the variability of our sample. So our sample in that previous example of BSU students in your dorm and how much they study, we got an average, but we can also get variability information, right? So our sample, we collected that data, we have all of that available. We can calculate our sample's variance, our sample standard deviation, our sample variability, the exact same way that we did way back in central tendency and variability when we first started talking about those ideas. So we can calculate the variability of our sample, and we can use that to estimate the population's variance. This logic works because the sample comes from the population, so it should have similar variance as the population. So for example, if the variance in your sample is very small, like your sample has very little variability, everybody's kind of giving you the same answer, not a lot of outliers. If your sample's variability is small, it's likely that the population variability is also small, and vice versa. If the sample's variance is large, it's likely that the population variance is also large. So think about how this works with real variables, with actual variables that we can think about. So say, for example, that we take our class as a sample of BSU students. So we take everybody who's in our class on the day after spring break, we come back and I give you guys a bunch of questions to answer, and you give me all your answers. So say that I ask you guys your perceptions of how busy you are during the school year, and say that when all of you give me your answers to this, that there's very low variability in your perception of being busy. So all of you are kind of giving me the same answer. Maybe you're all rating a 4 out of 5 or even a 5 out of 5 on that scale, and there's hardly any variability at all. If there's low variability in our sample, and our sample is you guys and your BSU students, then that low variability is probably true of all BSU students, not just you guys who are in our sample. So if our class has low variability on perceptions of being busy, that's probably pretty true of everybody at BSU, right? It's probably not something special about our class. Instead, it's probably just true of everybody. If I also asked you guys your current mood, there'd probably be much higher variability, right? So some people would be pretty unhappy, some would be pretty happy. A lot of people would be kind of in the middle there, but there'd be probably more variability there. So there'd be a wider range of answers, a larger standard deviation in your answers. And that also is probably true of all BSU students. So if you happen to be able to ask questions of the entire BSU population and you asked everybody their current mood, there would probably also be high variability there as well. So probably not the case that everybody would give me the same mood answer, instead probably much higher variability. So this is that same logic for why it works that we can use sample variability as an estimate of population variability. So whatever's true of the sample is probably also true of the population. And using that logic, we can estimate the population variance because we don't know it for sure. Because again, that's part of the qualification of using a single sample t-test is that you don't have population variance, but you do have population mean. However, there's an important caveat here to this idea of using sample variance to estimate population variance. And it's that we know that the sample variance is generally going to be slightly smaller than the population variance. So we know this. We could spend a bunch of time going into the mathematical proof for why this is the case, but that's more high level than we really need to worry about for this class. So basically just take my word on this one. We know, based on lots of mathematical proofs, that the sample's variance is generally a little smaller than population variance. So when I take you guys as our sample and give you guys the mood and the perceptions of being busy questions, whatever your variability is, it's just a little bit smaller than what the population's variability will really be. that means that it's not going to be exactly equal to the population variance. Instead, sample variance is a biased estimate of population variance. So biased estimate meaning the whole idea here is that we're trying to use our sample variance to be an estimate of population variance, but sample variance on its own is a biased estimate. So it's just a little bit off. So it's not going to be quite accurate. Because it's a biased estimate, we need to do something about that. What we need to do is apply a correction to try to get our sample variance to be a more accurate estimation of population variance. We need to apply a little correction to it to make it less biased. And the correction that we're going to do is actually going to be pretty similar to our correction for computing standard error of the mean. So remember when we first talked about standard error of the mean, we talked about how the standard deviation of the distribution of means has much lower variability than the standard deviation of the population of individuals. So when you draw those two distributions overlapping, right, the distribution of means is much more closely clustered around the mean. It's not nearly as variable. So because of that, right, when you're calculating the standard error of the distribution of means, you have to take the population variance divided by n and then square root it to get your standard deviation, or your standard error of the mean. So that kind of correction, that's a similar kind of idea to what we're going to do when we're estimating population variance. So similar kind of idea, we've got to apply a little correction in order to make it a better estimate of population variance. All right. So remember this formula for calculating sample variance. So think way back to central tendency and variability when we first talked about this. So SD squared, that's our symbol for sample variance, right? The squared tells you it's variance, not standard deviation, is equal to the sum of the squared deviations from the mean divided by n. So remember when we were calculating this in central tendency and variability, we made that chart with 3 columns, where in the first column you put your x scores, the second column you put your x minus m, so your deviation scores. In the third column you put your x minus m squared, so you square all the deviations. Then you add up all of those squared deviations, and then you divide by n, and that gives you sample variance. This equation, the one that's on the slide right now, this is still exactly how we're going to compute sample variance. So if I just want to know sample variance, that's the equation I'm going to use. But again, when we use sample variance to estimate population variance so that we can do a single sample t-test, we've got to apply a correction to account for that biased estimation. So it's going to end up not being this exact equation when we're computing estimated population variance. Instead, it's going to look like this. So this is the equation for estimated population variance. So you notice right off the bat that on the left side of the equation, it's s squared and not sd squared. That's very intentional because sd squared is sample variance, right? But when we're estimating population variance, we need to notate it differently so that we don't get confused on what's what. So to do that, we're going to notate it as s squared. So s squared is our unbiased estimate of population variance, or in short, you can just call it estimated population variance. To find estimated population variance, the top part of the equation here is the exact same thing as it is in the sample variance formula. So the top here is the sum of the squared deviations from the mean, and that's exactly the same as it is in the sample variance formula. So to find this, you're going to do that same thing where you make that chart with 3 columns, the x, then x minus m, and then x minus m squared. The bottom, however, is where it's different. So this is where our correction is coming into play. Instead of dividing by n, which is what you do for sample variance, you're going to divide by n minus 1. So the n minus 1, that's our correction. That's going to help us make sure that our estimate of population variance is more accurate than just sample variance alone. All right, so why the n minus 1 correction? Well, there's kind of 2 big reasons for this. One is that if you divide the sum of squared deviations by a slightly smaller number, that gives you a slightly larger answer. And the problem with sample variance as an estimated population variance is that it's a little too small, right? So sample variance is a little too small. So if we divide that in that equation, if we divide by n minus 1 instead of n, it's going to give us a slightly larger answer, which means our estimate is going to be slightly larger and it's going to be more accurate as an estimated population variance. So this idea where you divide by a slightly smaller number to give a slightly larger answer, think about 1 divided by 5, 1/5 is 20%, right? But 1/4 or 1 divided by 4 is 25%. So if you put a slightly smaller number in the denominator there in that lower part of the fraction, it gives you a slightly larger answer. So that's kind of the probably more easy to understand reason for why we do it this way. But we choose n minus 1 for a reason. So we don't do n minus 1/2 or n minus 2 or n minus 3. We choose n minus 1 in particular for a very particular reason. This term n minus 1 has a special name in statistics. We call it degrees of freedom. So you will often see this abbreviated as DF, which is just degrees of freedom. So it's going to be an important concept throughout the rest of the course here, especially as we're going through t-tests. So abbreviated as DF, that's degrees of freedom. And what degrees of freedom means, what DF means, is the number of scores that are free to vary. Now, fair warning, degrees of freedom is a really complicated concept. You need them for statistical estimations, for the test to work properly. You need degrees of freedom for that, but they're pretty high-level mathematical ideas. So fair warning, you do not need to completely understand why we need them for this class. I'm going to give you some explanations on the next few slides, but if you're not following it completely, don't stress out about it. Just make sure you know when to use degrees of freedom. So for example, in this case, you need it when estimating population variance in a t-test, as we'll see in a little bit here. So again, though, these are pretty high-level concepts. If you're not following the explanation on the next slide 100%, don't worry too much about it. Just make sure you know that degrees of freedom is n minus 1, and you know when you need to use it, even if you might not understand exactly why. Okay, but like I said, I'm going to explain it a little more just in case you're interested and in case you're able to follow this. So I said on the last slide that degrees of freedom are where it's free to vary, right? The number of scores that are free to vary. So what the heck does that mean? Well, think about it this way. This is kind of a silly example here. Say that you have 7 hats and you want to wear a different hat every weekday. So you have these lovely 7 hats at the bottom here, and you want to wear a different one every day of the week. So on day 1, when you're starting a new week, right, and you have all of these 7 hats to choose from, you can choose from all 7 of them. So you can choose any one of these 7. So you pick one, maybe pick that first one there with the little propeller on top. That's the one you wear on day 7, or sorry, on day 1. On day 2, because you want to wear a different hat every day of the week, you no longer have 7 choices. Now you have 6. So you've already worn the hat with the propeller on top on the far left there. That means that you can choose from the remaining 6 to wear on day 2. So you only have 6 choices now. So say you choose the witch hat on day 2. And keep going in this fashion, right? So on day 3, you can choose from the remaining 5, etc., etc. By day 6, you can still choose from the remaining 2. So say on day 1 you wear the propeller hat, on day 2 you wear the witch hat, on day 3 you wear the lobster hat, on day 4 you wear the cowboy hat, and then on day 5 you wear that awesome yellow hat. On day 6 now you have these last 2 that you can choose from, and you still have a choice here. You can still choose one of them, right? But by the time you get to day 7, you no longer have any choices left. So on day 6, say you wear, I don't know, what is that, train conductor hat? That's second from the right there. And then on day 7, if you want to wear a different hat every weekday, you no longer have any choices left. You have to wear the Santa hat if you want to wear a different hat on every weekday. So if we're going to apply this to this idea of degrees of freedom, in total for this example, this hat wearing example, you had 7 minus 1 or 6 days of hat freedom in which your hat choice could vary. So for 6 of the 7 days, you had a choice. On the 7th day, that last day, you no longer had a choice. Your hat choice could no longer vary on that 7th day. So your total hats were 7. Subtract 1 for the last day where you had to wear your last hat, and that means you had 6 days of hat freedom. That's kind of the idea behind degrees of freedom in statistics. That's why it's n minus 1, right? In the hat example, n is the number of hats you have, and that's 7. N minus 1 equals 6, so you have 6 degrees of freedom, and we're talking about hat choices in that example. So degrees of freedom, that's the same basic idea that we're doing in statistics. Now let's relate this back to statistics instead of just the hat example. When we're calculating sample variance and standard deviation in the z-test, when we're doing the z-test, so think back to what we were doing last week and the week before with that, we were not estimating anything because we had all the exact information that we needed. So we had the population mean, we had the population variance, we had all of our sample information. So in everything we've computed so far with the z-test, we've never estimated anything. So we have the actual information, we have the sample information, right? We got all that stuff, so we didn't have to guess at anything. We had it all. In the single sample t-test, right, we have the population mean and we have the sample information, but it's no longer the case that we have all the exact information we need because we don't have population variance. So that means that we have to estimate one parameter, so to speak. We have to estimate one thing in our test, and that's population variance. So we are estimating something now. We don't have population variance, we're estimating it. That means we're estimating one parameter. So when we compute sample variance then to estimate population variance, we have to correct for that estimation. That's why we do that n-1 to account for the one parameter we're estimating, and that one parameter is population variance. So hence why we have n-1, not n-2, not n-5, but n-1 for that one parameter we're estimating. All right, if you were following that, that's fantastic and wonderful. If you were like, what? That's okay, don't worry too much about it. Don't worry too much about the sort of high-level ideas in the last two slides here. Instead, just focus on knowing what DF means, how to find it, and when you need it. That's what you really need for the t-test, to understand the t-test. All right, so when we're estimating population variance then, we can rewrite that formula from a couple slides ago that we're going to use to calculate our unbiased estimate of population variance. We can rewrite it to incorporate that DF terminology. So now we have S squared. S squared again is our estimate of population variance. And that's going to be equal to the sum of squared deviations on the top there divided by DF. And of course, you know that DF equals n-1 for the single sample t-tests. For later tests, our DF is going to be a little bit different because we're going to estimate more than one parameter, but don't worry about that yet. We'll get there when we get there. We'll talk about that when we get there. All right, so basically, this is how we're going to do our unbiased estimate of population variance. S squared equals the sum of squared deviations divided by degrees of freedom. All right, now let's practice calculating this. On the board for this video lecture really just means in your notes. I've written out the calculations and I'm going to have them come up on the slides on the next two on the board examples we're going to do. So be sure you're following along and give it a shot to calculate them as we go. All right, so the first example here, we're going to practice computing an unbiased estimate of population variance for the following sample of scores. So if I'm using this sample to estimate population variance, then I'm starting at the beginning with this equation. Again, it's the exact same process on top as computing sample variance. On the bottom, then, it's just that the denominator is DF and not N. So again, think back to the central tendency and variability slides and the computations we did then to help understand how to do this here. All right, so I just scratched everything up here so I had room at the bottom for the calculations that I'm going to put in here. If you think back to when we did this in central tendency and variability, to make that chart x minus m, and x minus m squared, we first need to have the m piece, right? So we need the mean, and how we calculate the mean, as hopefully you remember, is it's the sum of x divided by n. So you add up all of your x scores. In this case, we have 6 x scores. Add them all up and divide by how many there are. So n in this case is 6. So when you're finding the mean, it's going to look like this. Add them all up, you get 74, divide by 6 because there are 6 scores, and your mean is 12.33. So that's the mean of your data here. We also are going to need, when we're doing our S squared formula, we're going to need DF on the bottom there, so we might as well find that right now. And DF, of course, is n-1, right? So in this case, DF is 6 minus 1, or 5, so our degrees of freedom is 5. Now that we have these pieces of information, we're ready to keep calculating and to make that chart, right? It's going to make that chart with the 3 columns. Put all of your x scores in the first column, and then your x minus m in the second, and then x minus m squared in the third. And when we do that, we get something like this. You put all of your x scores there. You do x minus m, so for the first one, it would be 10 minus 12.33, so your x minus m is negative 2.33. And then you square that in your third column, and negative 2.33 squared is 5.43. You keep going for all 6 of your scores there. Once you've got all of this, you're ready for the next thing, which is where you're going to sum up your x minus m squared. So remember, when you're calculating it like this, you find all of your squared deviations, and then you sum them together. So that's what that funky little e is, right? It means sum, so you add them all together. So by adding them all together in that column, you get a sum of 21.34. And then you're ready to plug everything into your equation, right? Your S squared equation there is going to be the sum of x minus m squared divided by df. So it's going to be 21.34 divided by 5, because 21.34, that's our sum of squared deviations. 5 is our degrees of freedom, and ultimately that gives us 4.27. So for this on the board example, when we're computing an unbiased estimate of population variance for this sample of scores, our unbiased estimate, or S squared, is equal to 4.27. Now keep in mind for this that your M is your sample mean, not population mean. So just keep that in mind. When you're doing your X minus M, you are not doing X minus population mean, you're doing X minus sample mean. So just keep that in mind. Make sure you've got those symbols down, that terminology down. Okay, for the second example, I'm going to recommend that you guys try this whole thing out for yourself this time. So feel free to pause the video right now while you work this out. You've got all of the numbers there. You've got 8 numbers this time. You've got all the numbers there. You've got the equation on the bottom there. So go ahead and pause this video and give it a shot. Once you are ready to check your work, press play and we'll go through it. All right, so you have hopefully paused it and you're ready to check your work now. So let's go ahead and do that. All right, so again, I just kind of scrunched this up so there's room at the bottom here. So again, when we're doing this, one of the first things we need to identify is M, so capital M, which is our sample mean, right? So for that, you do sum of X, you add all of your raw scores together, and then you divide by how many there are. For this example, when you add them all together, it's 21. There are 8 scores, so 21 divided by 8 is 2.63. So our mean here is 2.63. We also want to identify the degrees of freedom. So degrees of freedom, right, is n minus 1. There are 8 scores. So degrees of freedom for this example is 8 minus 1, which equals 7. So degrees of freedom is 7. Now we've got these pieces, we're ready to make that chart with our 3 columns, right, our computation chart. So we put all of our x values in the first column. The second column we put x minus m. So we take each of them, subtract the mean. So like that first one, 3 minus the mean of 2.63 is equal to 0.37, right? And then in that third column, you square that deviation, and so 0.37 squared is 0.14. You do that for all 8 of your scores. Once you've got that down, you've got all of your squared deviations in that third column there, then you're ready to add them all up. When you add all of these up, our sum of squared deviations is 5.91. And then you're ready to plug everything into that equation there. So you put your sum of squared deviations on top there, so you put 5.91 on top, divided by degrees of freedom, which we determined was 7. So 5.91 divided by 7 is about 0.84. And voila, that is our unbiased estimate of population variance. Okay, now remember, right, that this is the formula, this what's on the board right now, this is the formula for calculating regular old sample variance. So for example, the sample variance that you compute along the way to finding sample standard deviation, that's notated by SD squared for sample variance, right? It's got N on the bottom. Whenever you're calculating sample variance, that's the equation you're going to use. If, however, you're calculating estimated population variance, you're going to use this other equation, which is practice. So specifically for the single sample t-test, when we need to estimate population variance, that's when we're going to use the bottom equation here. We're going to notate it with S squared, so we know that it's estimated population variance and not sample variance. It's again, the top part is the same here, but the bottom is different. So the bottom, when you're estimating population variance, the bottom is degrees of freedom instead of N. So this is an important distinction, so make sure that you've got this down so that when you're calculating sample variance, you're using the top equation. When you're calculating estimated population variance, you're using the bottom one. All right, now when it comes to the single sample t-test and actually computing or conducting the single sample t-test, it's got some good news for you. It's the exact same 5 steps of hypothesis testing that we have used in the z-test. It's the exact same 5 steps. I didn't change, I just literally copied this from the z-test slides. It's the exact same steps, but we do have to incorporate some tweaks because we're estimating population variance. So we'll start talking about that today. We'll get through about step 1 and step 2 today, and then we're going to pick back up on this and finish talking about the steps on the Monday after spring break. All right, now step 1, which is to generate the research and null hypotheses. The good news is we do this exactly the same way as the z-test as we do for the t-test. There are literally no differences here. So we're going to identify your 2 populations on whatever your question is, whatever your example data is. Identify those 2 populations. So population 1, again, is going to be like the people who are in your sample. Population 2 is going to be like people in general. And then you use those to generate your null hypothesis. Remember that the null hypothesis has those 3 pieces of information you need. You need to state that there's no difference. You need to mention the 2 populations, so there's no difference between population 1 and population 2 on whatever the DV is. So you got to mention there's no difference, you got to mention the 2 populations, you got to mention the DV. But you do that the exact same way as we did in the z-test. And then you generate the research hypothesis. Again, the exact same way we did in the z-test. So again, it needs those 3 pieces. The research hypothesis says that there is a difference between population 1 and population 2 in whatever the DV is for that question. So step 1, there's no changes at all for the single sample t-test, exactly the same way as the z-test. Step 2 is where we start to see some differences. So step 2 is where we're determining the characteristics of the comparison distribution. This step 2 for the t-test is the same idea as the z-test, but it requires some different stuff. So it requires different procedures, different things that go into this, and we'll talk about exactly what that is. Now, because when we're doing the single sample t-test, because we estimate population variance, our comparison distribution actually changes. It actually changes what the comparison distribution is. So because we had to estimate population variance instead of knowing it, that means our comparison distribution changes. It's actually no longer just the distribution of means because we don't know population variance anymore. So for us to use the distribution of means in its original form, we have to know population variability so that we can compute standard error of the mean. Because we don't know that, we're just estimating it instead. It means that we've got to actually use a different comparison distribution for the single sample t-test. So for the single sample t-test, our comparison distribution is a t-distribution, not a distribution of means. So what is the t-distribution? It's the distribution of all possible values of t computed for random sample means selected from the population. That's a bit of a mouthful. It's actually not that different from the distribution of means. So remember, the distribution of means was all possible sample means from the population, like all possible combinations in groups of whatever the same sample size is, like in our M&M demo. The t-distribution is actually a similar idea, but it's a little different. So instead of all possible sample means, it's actually all possible values of t. And with that idea, all possible values of t, hold on to that thought for now, because on Monday when we come back, we're going to talk about what a value of t is, and we'll turn to this idea then. So hold that thought for all possible values of t. But basically, it's all possible values of t computed for random sample means selected from the population. So that second part of the definition there, random sample means selected from the population, that's the same basic idea as the distribution of means. So we use the t-distribution basically the same exact way as we use the z-distribution and as we use the distribution of means. So we're going to end up labeling the region of rejection. So we're going to find our cutoff score, right? And we're going to label that in our distribution, shade in our region of rejection in the tails, find a t cutoff value, a critical value to do that. We compare a t obtained that we get in step 4 to t critical so that we can make a decision about whether to reject the null. We're going to talk about all of this in detail in case you're like, wait, what was that? Don't worry about that. We're going to talk about it in detail. But basically, the idea is that we use the t-distribution. It's just a comparison distribution. We use it the exact same way that we use the distribution of means, with just a couple of little tweaks to incorporate the differences in the t-test. Now again, this definition of the t-distribution, we're going to come back to that on the Monday after spring break and talk about a little more then as well. All right, now remember this slide from the z-test. This is not the t-test information. This is from the z-test. So when we talked about the z-test, we talked about how the comparison distribution for the z-test is the distribution of means. We have to identify those 3 pieces of information. So we need the shape of the distribution. The distribution of means is always normally distributed. We know that because of the central limit theorem. We need to know the mean of the comparison distribution, and the mean of the distribution of means is the population mean. And then we need to know the standard deviation of the comparison distribution. The standard deviation of the distribution of means is the standard error of the mean. So remember, for the z-test, the central limit theorem tells us these pieces of information. For the single sample t-test, when our comparison distribution is not the distribution of means, but is instead the t-distribution, it gets just a little bit different. So in the single sample t-test, the characteristics of the t-distribution, we actually still need to determine 3 characteristics. So we need to determine the mean of the t-distribution, and this actually is the same as it is in the z-test. So when you're using a t-distribution as your comparison distribution, the mean of the t-distribution is still equal to the population mean. So just like in the z-test, the mean of the t-distribution equal to population mean. So we don't need to do any calculations in this, right? We're just identifying what the population mean is. That's the mean of our comparison distribution. This is where it starts to get a little different. Our standard deviation now has to be, a standard deviation of the t-distribution now has to be estimated based on our unbiased estimate of population variance. So remember how we computed standard error of the mean for the z-test. So think back to the z-test. How we computed standard error of the mean for the z-test. It was sigma squared divided by n square rooted to get standard error of the mean. And sigma squared is the symbol for population variance, right? But we don't have that for the t-test. We have to estimate it. That's our s squared. And that means that we need a new equation for the t-test that's going to reflect our estimation of variance. We'll talk about that on the next slide. So standard deviation is again a characteristic of the comparison distribution we need to identify. It's just going to get calculated a little bit differently from the z-test, but otherwise you're still identifying it. Now third, and the one that might seem the weirdest at first, is that the shape of the distribution for a t-distribution is actually not necessarily normally distributed. So whereas every time we did the z-test last week and the week before, we always did the shape first because the shape was always normal, because the central limit theorem tells us that, that's no longer the case in the single sample t-test. And we'll talk about that in a couple minutes after we talk about standard deviation. So we'll talk about that in a little bit here. But first, let's talk a little more about the standard deviation of the t-distribution. So we talked about how this has to be estimated based on our unbiased estimate of population variance. Let's talk a little more about how we actually do that. All right, so standard deviation of the comparison distribution. Remember for the z-test, last week and the week before for the z-test, we computed standard error of the mean based on population variance. So we use this equation here, our sigma sub m equals the square root of sigma squared over n. Talked about how sigma squared, this is population variance, but when we're doing a single sample t-test, the whole reason we're doing the t-test instead of the z-test is because we don't have population variance. So we don't have this piece of the standard error in a t-test, which means that we cannot use this equation to calculate the standard deviation of the comparison distribution for the t-test. So for the t-test, we actually have to use our unbiased estimate of population variance instead of actual population variance to compute what we call the estimated standard error of the mean. So in case you're getting confused with all of these terms, the equation that's on the board right now, that's for the z-test. It's the standard error of the mean, where you use the actual population variance to compute. In the t-test, we don't have the actual population variance. We estimate it based on the sample variance. That's that s squared we were just talking about before. That's what we have to use when we're computing standard error for the t-test. And because we're using an estimated population variance instead of the actual population variance, we're not actually computing standard error anymore. We're computing estimated standard error. So just like our s squared is the symbol for estimated population variance, we also need to have an estimated standard error of the mean. All right, so here is how to compute estimated standard error of the mean for a single sample t-test. It's this equation here. It's s sub m. That's not s times m, right? That's s subscript m. So s subscript m equals the square root of s squared divided by n. So this is, as you might have noticed, the same idea as it is in the z-test. So it's the exact same structure of the equation. So in the z-test, on the left side, it was sigma sub m, whereas in the t-test, it's s sub m. And then in the z-test, the top of the equation on the right side was sigma squared, whereas in the t-test, it's s squared. Otherwise, it's the same basic formula. You're just using different symbols because this time they're estimated values and not known values. That's really the only difference here. So to put definitions to each of these pieces, your s sub m in the left side of the equation here, that's your estimated standard error of the mean. To calculate that, you need to take your estimated population variance, your s squared, the one that we practiced calculating a little bit ago, that's what this is, s squared, divided by n, which is sample size, and then square root it. And that is how you get estimated standard error of the mean. So again, for the t-test, we're using our estimated population variance, the same way we calculated it a couple minutes ago in this video lecture with that DF correction. And then you're dividing by n. Now importantly, in the estimated standard error of the mean calculation, you're not dividing by DF, you're dividing by n. So make sure you keep track of when you're using DF and when you're using n. So in the estimated standard error of the mean equation, you're using n. So you take an estimated population variance divided by n, square root it, and voila, that gives you estimated standard error of the mean. All right, so let's practice this real quick. Again, on the board, which really just means in your notes in this class. So we're going to do two examples on the next slides. I'll go through the first one pretty quickly, or rather, I'll just go right through the first one. The second one, I'll give you a little time to pause and work it out yourself to check your answers. All right, so let's practice computing estimated standard error of the mean based on the same sample that we used in the previous on the board number 1 example. So here are those 6 numbers again, 10, 13, 14, 12, 15, 10. When we calculated the estimated population variance a couple slides ago for this example, that previous on the board example, we found that the estimated population variance was equal to 4.27. So if now we're going to compute the estimated standard error of the mean, then we need to use that bottom equation there. S sub m equals square root of s squared divided by n. So this is quite easy to just plug and chug. Basically, you're just going to rewrite it and put the numbers in. So s squared we know is equal to 4.27 because s squared is estimated population variance. So that's 4.27 that we calculated before, divided by n. N is the sample size, and in this sample there are 6 numbers, so our sample size is 6. So the square root of 4.27 divided by 6 is equal to 0.84. That means that our estimated standard error of the mean is 0.84. So not so bad, right? You're doing a lot of the work ahead of time in the s squared calculation so that when you get to the estimated standard error of the mean, it's very simple to just plug and chug. All right, here is our second example. So this is those same 8 numbers from the on the board number 2 from previously. So now we're going to practice computing estimated standard error of the mean with this. So again, you're going to use that equation on the bottom there. From the previous on the board, we had found that the estimated population variance was equal to 0.84. So you can go ahead and pause the video, take a minute to work this through for yourself, plug things in, calculate, get your estimated standard error, and then check it on the next screen. So I'll give you a second to pause your video and work this out. All right, so presumably you have done the calculation for yourself and you're ready to check your work now. And here it is, right? So again, you're just plugging and chugging. So for this one, the estimated population variance, which is s squared, is 0.84. We divide by n, which is how many scores there are. And in this example, n is 8. So 0.84 divided by 8 and then square rooted is 0.32. So it's telling us that for this data, the estimated standard error of the mean is 0.32. So not so bad. It's just a little bit different than the z-test. Again, the only reason it's different is because of that estimating population variance. Because we had to estimate population variance, it means that the standard error changes a little bit to estimated standard error, but otherwise the format is pretty much the same. Okay, that brings us to our third characteristic of the t-distribution, and the last thing we'll talk about in this video lecture. So we know that the mean of the t-distribution is equal to the population mean. We know that the standard deviation of the t-distribution has to be estimated. It's the estimated standard error, right? Now that we know all of that stuff, we're ready to talk about the shape of the t-distribution in a little more detail. All right, now in z-test, what we spent the last couple weeks talking about, we talked about how the distribution of means, which is our comparison distribution for the z-test, is normally distributed. It's always normally distributed because the population is normally distributed. So we talked about how we know this because of the central limit theorem. The population itself is normally distributed and most variables are normally distributed. So the central limit theorem tells us that the distribution of means is also normally distributed, and that therefore our comparison distribution is normally distributed. In the t-test, though, it's a little different. So in the single sample t-test, as we've been talking about so far, we had to estimate population variance, right? So we estimated it based on sample variance and sample size. So that is our estimate of population variance. So remember on the top there, right, it was your sum of squared deviations divided by, on the bottom, it was your DF, right? So it's based on sample variance as well as sample size. So we estimated it. But because we estimated it, that means that we have more room for error due to the fact that we estimated it. So this time in the t-test, it's a guess, right? It's our best guess about what the population variance is. It's not exact like it is in the t-test, or sorry, in the z-test when we actually know the population variance. In the t-test instead, we have more room for error because we estimated that, because we don't know it for sure. And because we have more room for error, that means that we cannot assume that the t-distribution is normally distributed. So in turn, because we have more room for error, because we estimated population variance, that means we cannot assume that our distribution is normally distributed. In fact, mathematically speaking, there is a higher frequency of extreme scores in a t-distribution compared to a z-distribution. So in a t-distribution, mathematically speaking, there's a higher frequency of extreme scores, or rather extreme means. We'll talk about what that looks like on the next slide here. So mathematically, there's a higher frequency of extreme scores, right? Here is what that looks like. So this I took from the book, this image from the book. The black line, as you can see, that's a normal distribution. It's got those nice little tails and the hump where the mean is. The two blue dotted lines are two different t-distributions. So again, t-distributions are based on estimated population variance. Mathematically speaking, we know that using estimated variance doesn't produce a normal curve in most situations. Instead, there's a higher frequency of extreme means or extreme scores in the tails. So higher frequency meaning, again, remember this distribution, this is a frequency distribution. So if you look back at the black distribution and the tails of the black distribution, they're very close to the x-axis, which means that they are very low in frequency because, again, the y-axis is frequency here. So they're very low on the y-axis, they're low in frequency. If you look, however, at the blue dotted lines, our t-distributions, those tails are nowhere near as close to the x-axis, which means that they're heavier, right? There's a higher frequency of extreme scores, so they're higher up on the y-axis. Basically, it just means there are a greater number of extreme scores in the tails compared to in a normal distribution. So when we say mathematically there's a higher frequency of extreme scores in a t-distribution, this is what we're talking about. We're talking about these tails being higher up in frequency. In other words, there are more scores in the tails than there are in a normal distribution. All right, now why are there two t-distributions shown here, you might be wondering? Well, remember from earlier, we said that in the single sample t-test, we had to estimate population variance based on sample variance and sample size. That means that we have more room for error due to our estimation, so we cannot assume the t-distribution is normally distributed. Instead, mathematically, there's a higher frequency of extreme scores, right? It turns out this follows a very particular pattern. So in fact, the smaller the sample size, the greater this tendency is. And that's because we use sample size to estimate population variance. So the smaller the sample size, in other words, the smaller the number of people in your sample, the fewer people you have in your sample, then that means a higher frequency of extreme scores that we get in the tails of a t-distribution. It works out that way because we use sample size to estimate population variance. So remember that equation for estimating population variance, where it's s squared equals the sum of squared deviations divided by degrees of freedom. Degrees of freedom in the denominator is n minus 1, which means that n is a big part of your calculation, and n, of course, is sample size. So it turns out that the smaller your estimation, or the smaller your sample size is, the smaller your denominator is, the greater the tendency for there to be heavier tails in the t-distribution. So the smaller the denominator in the sample estimated population variance equation, the more it affects the distribution. If you're wondering why this is, again, you're just going to have to trust me on this one. These, again, are pretty high-level math concepts for why it works the way it does. For the purposes of this class, you don't need to know why. You just need to know that this is a thing that happens. So as long as you know that the t-distribution has heavier tails, you're good to go. All right, so all of this means, again, right, that the t-distribution is not normally distributed because it has heavier tails than a normal distribution. So we talked about how what exactly it looks like depends on sample size. To be more specific, it depends on degrees of freedom. So the bigger the sample size, the closer to a normal distribution, whereas the smaller the sample size, the heavier the tails get. So this is that problem with the t-distribution. And this is why we cannot say in step 2, we cannot say that it's a normal distribution for our comparison distribution because it's not. So typically, or at least when you have a smaller sample size, it's not normally distributed. It doesn't follow that same pattern as it did in the z-test. All right, so because we estimated population variance and that's based on sample data, our estimated population variance can be pretty different from one small sample to another and different from the population variance. That inconsistency then is what produces a t-distribution that's only approximately normal. But importantly, the bigger the sample size, the bigger samples we use, the closer we get to a normal distribution because we're getting closer to the true population variance by including more scores in our sample. So that's the importance of sample size. If I only take 5 people and I get, I don't know, their mood score or something, and I compute my sample of 5 people, whatever their variability is, if I'm going to use my sample of 5 people to estimate population variance, those 5 people might have a pretty different variance than the population itself. Whereas if I take a sample of 50 people or of 500 people and I get their mood scores, then whatever their variance is of the 500 people, for example, whatever that variance is probably a lot closer to the real population variance. So sample size matters a lot here. The bigger the sample, as sample size increases, our t-distribution becomes closer to that of a normal curve. All right, so all of that is to say that step 2, where you're determining characteristics of your comparison distribution, is a little bit different than it is in the z-test, right? So all of that to say that our characteristics of the t-distribution, there is again 3 of them. It's the characteristics you're determining are the same characteristics, mean, standard deviation, and shape of your comparison distribution. But because it's the t-distribution, it's a little bit different than it was when it was the distribution of means. So for the t-distribution in the single sample t-test, you need to determine the mean of the t-distribution, which is equal to population mean, so no calculation there. You need to determine the standard deviation of the t-distribution, which you have to calculate. It's the estimated standard error of the mean using that equation from earlier, right? Our S sub m, that's the estimated standard error of the mean. And then you also need to determine the shape of the t-distribution. And for the purposes of step 2, all you have to write is that the shape is not normal. So whereas in the z-test, every time we wrote shape equals normal, for the t-test, you're writing shape equals not normal. The non-normal shape of the t-distribution affects a later step, but we're going to pick back up on that after spring break. So for now, just keep in mind the t-distribution is not normally distributed. So on the Monday after spring break, we're going to pick back up on this and talk about how that affects other steps of the t-test, go through the remaining step 3, step 4, step 5, and do some practicing, and jump right back into it. All right, so remember homework number 17, this is going to be due the Monday after spring break, so be sure that you have this on your radar. You don't forget to complete the homework number 17. For homework number 17, question number 1 here is to calculate estimated population variance for the following set of sample scores. So remember estimated population variance, that's our S squared in that equation from earlier. So use that equation to compute estimated population variance for this set of scores. Don't worry about estimated standard error yet, but you can if you want to. Question number 2 then, why is the t-distribution not normally distributed, and explain your answer. So write me at least a couple sentences here about why the t-distribution is not normally distributed. Again, if you're a little stumped by this, or if you're finding this idea confusing, this again is a great place to go back and read the textbook. So read the section of the textbook. The more exposure you get to these ideas, the better off you'll be, the more you'll understand them. So feel free to watch this video lecture a couple times, look through the slides a couple times, all that kind of stuff. And if you've got questions about things, then definitely bring them to class the Monday after spring break. We'll spend a little time talking or fielding questions from the video lecture of things that might have been a little confusing. So definitely write those down, bring them to class that Monday, and we'll chat about it then. All right, now next slide is going to be the exit ticket. So today's exit ticket, 2 questions. One is that we compute t-test instead of z-test because we're missing a key piece of information. What piece of information is it that we're missing? And then question 2, what does DF stand for? So the exit ticket is the only thing that's a little bit different because typically we turn it in at the end of class, right? But today there's no physical class. So what you're going to do is you're just going to bring your exit ticket with you with your homework and turn them in at the same time on that Monday after spring break. So hopefully that makes sense. If anything's confusing here, feel free to email me. I'll be a little slow to respond, but I will respond. So if anything's confusing about this procedure, just let me know. Otherwise, that Monday after spring break, bring your homework, bring your exit ticket, review the slides or your notes right before class, and we'll pick back up on it then. All right, so this is the very last slide here. Again, just remember homework number 17 and today's exit ticket are due on Monday, 3/12. And then in the meantime, hope you guys have a great spring break. So have a good week off, and we'll chat with you in a little while.